So the agenda today is just to go over what we're trying to do here, frame it a little bit. We do want to have a look at the evolution of HD radio a little bit. Kirk's presentation was a great overview as to where we are. We're diving a little bit more into the details, some of the technical nuts and bolts. But it's important to know where we came from to understand where some of the current problems and challenges are. We look at a little bit more at the FM HD1 time alignment problem and why this is a problem in the industry. And then we'll look at how we solved it. With that, I've got a couple of demo clips on here. Hopefully, I can show those to you here, and talk a little bit about how we can roll out this new architecture I'm talking about across a wider fleet. And then lastly, there's a few discussion topics about IT security. We're talking all about IP connectivity here, and I think that will lead nicely into our next discussion topic. So hopefully we'll see a few questions. So first of all, why would Nautel be talking about virtualization, the cloud? After all, a transmitter can't virtualize that. It's an AC to RF converter for all intents and purposes. So why are we talking about that? Well, especially with the presentations over the last 2 days, it's very clear there's a lot of change happening in the way we build studios and the way we build whole radio stations, and we need to be able to keep up with that change. So we see a lot of that change in the way cloud services are offered, how software air chains are happening, and we believe the interface into the transmitter, that is where we can come in, where we can contribute, where we can add innovation. So we're more focused on the connectivity from the cloud into the transmitter. So we're not going into some of the details like Radio Cloud was talking about yesterday or wide orbit. So we're more or less, the egress from the cloud, if you want to look at it that way. So our purpose, or what we really wanted to set out to do, is build a transmitter that has all of its modulation content over IP, every last bit. We just want an Ethernet jack, ideally 2 Ethernet jacks. And we can do that with a synchronous IP link, and we can connect that to a cloud-based or a local backup, and we'll show you the details in a second. So broadcasters are telling us HD is very complex to install, so how can we make it simpler? So that's one of the goals here as well. Traditional studios are going away. So can we come up with a way to be platform agnostic, location agnostic, and can we come up with a platform that can handle analog today and optionally add in HD? I think that's particularly an important topic here for Canada, where the direction of HD is still, we'll see which way it's going to go. But we want to come up with an architecture that can handle HD, but doesn't necessarily require it today. Reliability is another thing we want to look at, and we're going to present how we can have multiple air chains feeding into one transmitter and do changeovers. In particular with HD Radio 2, like I said, there's a lot of change in the way we're going to be building equipment and the way it's all coming together, and we're hoping to lower the entry into HD radio. So if the business case for you isn't entirely clear, maybe we can lower the hurdle to get into it, and perhaps that drives adoption a little bit. A little bit of history, but I don't want to dwell too much on it. Some of you might have seen the box on here. We call it the NEI box. That was the second generation HD radio exciter. It's probably vintage 2005. It's still used in the AM applications with some manufacturers. So that's the second generation. And it was a single box that took the HD1 audio in, did all the encoding in the exporter function, the modulation in there, and then there was a connection into the exciter to add it into the already existing FM audio chain. So really at that point, HD was a bolt-on. It was all at the transmitter site, but it was a fairly simple, easy box. But at that time, we were not too worried about time alignment yet. The next generation, third generation, now we're talking 2007 time frame. The modulator was broken out into an add-in card into the exciter, the X-Gen card. You might have heard that term before. That is now sitting right in the exciter. And Xperi, or Ubiquiti at the time, introduced the E2X protocol that already handled all things HD related. So the entire modulation for HD was encapsulated into that exporter to X-Gen E2X protocol. But it did not handle the FM. Again, HD was a bolt-on to the existing FM installation, So the FM was not handled here at all. The complicating factor now is if you move the exporter back to the studio, the differential paths between the FM and the HD, between where the audio splits and until it rejoins in the exciter, those are long paths, depending on the STL environment, whatnot. So there was lots of chance of slip between the FM and the HD1 simulcast. We'll talk about that diversity delay alignment issue in a second. It just became a lot more challenging in that architecture. So we've just mentioned the NRC was looking at a time and level guideline. That guideline with the 4th generation strongly recommends putting all your equipment at the transmission site. That is, with today's architecture, is the best way of limiting how much the FM and the HD1 shifts with one another. So 4th generation is defined by the fact that the importer and the exporter is now a single box. Where previously there were 2 separate boxes, now it's one box. But really, high-level architecturally, not much really changed. If you look at it from the 20,000-foot level, the equipment changed, the implementation changed, but fundamentally not that much. The addition that happened here is that we introduced receivers that look at the off-air signal, look at the time delay between FM and HD1, and can add a delay line to null out that delay. So that was one addition, not strictly related to that generation, but it's something that happened along the same time frame. So let's talk a little bit about the FM HD1 time alignment. So, of course, if your FM and the HD1, your receiver first acquires the FM, plays the FM, takes a few seconds before the HD is acquired, and it will blend over to the HD. If the audio is off by seconds, of course, you're going to miss entire words, or you're going to cut out entire words. It becomes very apparent. But even if you're pretty close into the millisecond, microsecond range, there's artifacts. So what happens is I've plotted the frequency response as to, depending on how far the delay is off. The top picture, the delay is off by 3 samples, and it doesn't matter if the HD leads or lags the FM. 3 audio samples, that's 68 microseconds. That's a pretty tough spec to meet. If you're running 2 audio paths over 2 separate STLs, different audio processors, it's tough to get it to within 68 microseconds. But at 68 microseconds, what happens is as one audio ramps down, the other ramps up. At some point, you'll essentially get a comb filtering effect, and it will null out about 7 kilohertz. But your main audio content's not affected yet, so it's not as noticeable. Once you slip out to 12 samples, it shifts down into your main audio content, 2 kilohertz, and there's more notches that are happening, more comb filter notches. As you're out to 50 here, then it becomes very apparent. The interesting thing that happens when you slip out further, like 300, it almost becomes a little bit better, in a sense that's unlikely that your entire audio is going to be nulled out, because they're becoming very, very selective. So the message here is either you hit the bullseye, less than 3 samples, which is the NRC specification, so we should strive for that. But if you can't meet that, you might almost be better off a few milliseconds. So the danger zone is actually really close. And the sort of artifacts you can expect, the ones I've heard, I would explain them as maybe swooshing sounds, maybe a quick mute. But if the car is driving on the fringe and you're going in and out of HD, it can become very apparent. And people have taken cars back to the dealership. Hey, my radio's broken. So that is certainly an issue. So with some of the equipment that's on the market today, here's some captures with an Innovonics Justin receiver. We can log the differential delay over time, and that is taken from the NRC guidelines. Top one would be the exporter back to the studio across a typical STL, not locked to a 10 megahertz GPS reference. And you can see it's going by hundreds of samples. You can't hit that 3 sample window that I've drawn in there. It just moves all over the place. Even if you plug in at 10 megahertz on both sides, there's still temporary variations that makes it very hard to get that 3 sample perfectly. It is better, orders of magnitude better, but it's still not ideal, potentially. If you put a lot of care into your installation, it is possible to get good time alignment, but you have to watch it, and that guideline will certainly help you. Another aspect that you need to know about with those receivers that you can measure the off-air delay and add an automatic delay line. Well, they've also built that into receivers now. So some of the newer automotive receivers will actually try to null out the delay because it's been such an issue in the industry. But now you have two control loops cascaded, and that can lead to instability. So if your broadcast plant is moving too fast, and your receiver's trying to keep up with it, it may just give up. And what happens is, if the receiver can't achieve solid lock, some of them will entirely turn off your HD. So you've just done an HD conversion, and the receiver won't even play it. Now that's only some of them, but it's going to be a more prominent class as we move forward. So the latest update to the NRC specification put limits as to how fast you can change the broadcast plant delay, but it also limits the effectiveness of that method. So we wanted to solve the problem more definitely. And we believe the answer is what I call synchronous air chains, where everything is synchronous. Now, what do I mean with synchronous? I'm coming from a DSP background. It's just numbers of samples, each one occupying a fixed amount of time. And in a synchronous air chain or a synchronous chain, DSP chain, you'll never lose a single sample. And you can account for each sample. There's a fractional relationship between all processing stages. So, for example, if you look at our typical air chain today with the exporter on the left going through the XGen and the exciter, it is the exporter that's the heartbeat of the entire system. So if you have that hooked up to the GPS gives you a 1 pulse per second. We turn that into 10 megahertz, so exactly 10 million cycles per 1 second. We then turn that into a 44.1 word clock, exactly 44,100 clocks in 1 second, or 10 million cycles. The IBOC modulator, or the exporter rather, takes 64K audio samples. It creates an L1 frame out of those, and there's no test on those numbers, don't worry. But the point is, no matter what point in the chain you're looking at, there's a fractional relationship of all the transformations. And you never lose a sample, or if you do, it's a system issue. And that ripples all the way through to even the DAC. Now, this is just an example architecture. Different options are available. But if you have a direct-to-channel modulator, it ripples all the way through. So in the end, it is the exporter that dictates your carrier frequency, because it's all pushed forward. So in the current system, the synchronization flow follows the content flow. What we're doing is we're flipping it around. We're saying there's already a really high quality crystal in the exciter, and it can be connected to GPS if you desire to do so, but it's already calibrated. It's all within specifications already. So we want to synchronize back rather than forward. The second realization is we wanted to increase the air chain to now include the audio processor. And the reason for that is now we have one entry point into the air chain where the FM and HD1 are still joined. It's one main audio feed. We haven't split it yet. And it will go through two separate paths synchronously through the entire chain until it's recombined. And because we never lose any samples, they will always stay lockstep. So that's, in a nutshell, that's what we're trying to do. Key of the whole concept here is, as we're talking about the IP link, we wanted to come up with a transport protocol that carries the entire modulation. Like I said before, we want one Ethernet jack to carry the entire content, or ideally two. So if you look at the protocols involved today, on the bottom we have composite MPX. It's already carrying several services, if you want to think of it like that. Left plus right, PIDE, left minus right, RDS, potentially subcarrier modulation. The same thing with the E2X protocol. It carries your HD1 encoded audio to HD4, program service data, artist experience, station logo. So we kind of see the E2X at the same point in the air chain as composite MPX. They're kind of, they're buddies. So all we ended up doing is create a protocol that intersperses composite MPX with the E2X through a pipe, and the two can't move from one another. So they're locked in time using the synchronous mechanism. So they can't shift anymore. We've locked them in place. So now we no longer have to keep all of the equipment at the transmission site. It allows us to move the equipment wherever we would like, and it could be the cloud. And we can demonstrate that we have perfect time alignment for all of these processes as we go through. I'll just spend a quick second on that. That's from the paper here. And by the way, if you would like a hard copy of my paper, I've got a couple here. If not, I can also send you a soft copy. But if you look at the different architectures, with the synchronous air chain being on the top right, really we're only left with the transmitter at the site. I mean, that's kind of the goal we're striving towards too. And you have a lot more boxes at the transmission site as you sort of dial back the various generations. In terms of STL bandwidth requirements, composite MPX takes quite a bit of bandwidth if you don't compress it. In our case, it's about 2.8 megabits. But we could consider applying codecs for composite MPX. There's micro MPX, and I believe there's also aptX. So, two competing compression algorithms, and they can bring it down to a couple hundred kilobits. So that's certainly something we can have a look at. Overall, I think it's very comparable to the other architectures. Let's move along. So to put this all together here, it looks complicated here in comparison to the other block diagrams I've shown here, but keep in mind, I'm showing 1, 2, 3, 4 different air chains here. And I'll simplify it, so, I'll break it down. But we've got, essentially, it kind of mimics the demonstration we had set up at NAB, where we had one air chain in the cloud, in AWS. We had one essentially running on our HD multicast platform, right beside the transmitter. That was the backup air chain. And then we had a separate one on the booth that we consider the on-premise air chain. And we're able to switch back and forth between all of those. I'll get into that a little bit more in a second. One thing that we've added with the synchronous concept, we have all these buffers in our modulator now. But like I said, we're flipping around the synchronization back towards the air chain ingress. So we came up with an algorithm that essentially tells the audio processor at where the FM and HD1 gets sampled to either slow down or speed up ever so gently. So if our buffers run high, we say, okay, hold on, don't go quite so fast. If they run low, we say speed up a little bit. And in doing so, we can achieve a target buffer level. And we can set that to whatever we want to do. But this allows us to have multiple air chains with content ready to go. But let's simplify this block diagram a little bit and talk about, sort of the components that we've put in here. So the key part in the air chain that we've added, on any one of those on the left, we have a partnership with Telos where we've integrated essentially the Omnia 9 platform, now labeled Omnia for Nautel, and we've combined it using a glue layer that we've implemented with the buffer control and the synchronization. We've combined that with the Xperi Gen 4 software. In the end, it's essentially one software build now. Where we've married the two together. And that's essentially the key of it. And with that, we can run that in various air chains. So I don't have to speak too much about the Xperi software. Certainly, Xperi could talk about that, but it is the standard release that they give us. And the only thing that we've added is the synchronous audio interface that drives the synchronization. But again, I want to highlight, now we've removed all hardware dependency. It's a true software build, and we can run it in the cloud. As it's standard Xperi software, we're able to very easily combine it with Rapid. At the NAB show, Xperi set up us with a demo feed. A few IP address changes later, we had it on our transmitter. That was pretty easy to set up. The Omnia for Nautel, so that's the piece of software that sort of is the front end of it, and it's a really key component to this architecture. And really, I'm not going to do justice talking about all the features that it does. I mean, please talk to Telos about that, because I'm only scraping the surface on that. But the key thing is it's a dual processor for FM and HD. So one input, dual output. And we can feed it with live fire shoutcast, and it's got a built-in RDS generator. Just a quick shot of the AWS control panel. It's essentially just a Windows instance that's running in there. We've installed the software. After all, the cloud is just someone else's computer, right? So it's running a Windows instance right now. We can consider Linux down the road as well, but currently it's a Windows deployment. And it's so nice. You can just clone the system. You can move it to a different data center in AWS. We had a demonstration where we had one set up in Ohio, another one down in Sao Paulo, and changed over between them, and the diverse delay stayed fixed. But your STL path went across the world, and it still works. And essentially in that Windows instance, like I mentioned, we're running those two software components. Just a couple of notes on the AirChain selector. So that is a piece that we've added to our modulator, and it's got all the buffers. You can see the buffer levels that are there with the ones that are connected. It tells you which one is the active AirChain and which ones are sort of standby. You can either set up in manual mode where you can say, okay, disconnect this one, reconnect this one, and there's a bit of a priority list. The top most on is the highest priority, and it goes down from there. So there's a couple different connection methods. One I call a cold standby, where we have not connected to the cloud, where we have not connected to the AirChain. But if anything goes wrong, we'll have to initiate the connection, fill the buffers, and then we can bring it online. So there could be a short outage, but important enough, it's before the modulator, so there's no RF drop. So it would just be silence on the FM carrier and the HD. So the RF, the power level stays unchanged. Then we introduce a hot standby, where you're already connected, the buffer is full, and you can just switch over. And we've got a special alignment mechanism where we can minimize your HD downtime to about 3 to 5 seconds. And multiple TCP, if you can have two IP addresses associated with your AirChain, we can use both of them. And if one of those goes, and through routing, you can set it to different STLs. So if the entire STL goes down, it's a hitless change to the other one. No impact to the broadcast. So that's the last one we're looking at here. Now here's something really, really neat. Not only do we fix the FM-HD diversity delay, but if you're changing over on an HD receiver, it's graceful. So it needs a little bit of explanation here. On top, the top plot is the time alignment, and it just sits at 0. Kind of boring, but had to show it. So it always stays perfectly aligned. It's only a 60-second shot, so I kind of had to do things really quickly. But at the 60-second mark, I essentially killed one of the AirChains. And you can see the red is the FM on that particular plot. It goes away right away. But as you notice, from about 58 to 55 seconds, the HD keeps playing. And that is because of the diversity delay in HD, there's buffering in the receiver. So even though the RF is done, your radio keeps playing for another 4.5 seconds. That's part of the HD system. So the HD keeps on playing, and then at that point it will drop back to the unmodulated FM. The new AirChain comes on, and I put it at a lower audio level so we can see which one is currently active. The FM comes first, and then it blends into the HD perfectly aligned. Now that's the cold switch. The hot switch, again, that's about 25 seconds. You can see I'm switching over to the other AirChain with the higher loudness level. The FM does it instantly, but it keeps on playing 4.5 seconds HD. Now what happens, the blend process will ramp down the HD, it will ramp up the new FM audio, so we actually achieved a crossfade when you're switching inputs. Now, Xperi did that for us, can't take the credit for that. And then once it acquires HD lock again, it will blend back into perfectly aligned audio. So I'm hoping to see if you can see that in some of the examples here. There's a lot to look at here, and hopefully the audio will come through. So in the top left, you see the AirChain selector that I just mentioned. Our AUI control of the transfer in the bottom right. A 12-year-old Polk audio receiver I happened to find in the lab. And on the left is the time alignment plot, as well as the audio levels, so you can see that. And I've put a couple clues on there. Hopefully we can see how that all happens. So I've got a total of 5 air chains set up here. And let's just get moving on that. Our main air chain right now. We've just killed the main air chain, and that's the second TCP link. There's no hit. Audio keeps playing. It's running on the second air chain. Now, when that is killed, we're going to the backup air chain. Same audio, but not different air chain. Oh no, right, it was different audio. But you can see it stays locked. You can see the DQ plot tells you when the HD is back acquired. Once it's 90%, it's playing again. So it's only a momentary HD drop. Now we're killing the backup air chain. See if it switches over to the cloud. So now it's reaching out to AWS. You can see the different audio. It was just a very smooth transition. That is that crossfade I was talking about. And throughout all that, it stays almost perfectly aligned. Plus minus 1 measurement errors. I'm good with that. And see, I've put different PSD in there, so it tells you it's coming from the cloud. Now we can also support legacy exporter in this architecture, but they don't know anything about those air chains, so I just put a test tone on it. But it could serve as a final block. So in this case here, that's the HD multicast on top here. That's the first 2 connections. And I'm disconnecting an Ethernet cable just to show a complete failure rather than just disconnecting. Again, no hit, it's going through the other cable. But once we disconnect the second cable, of course, it has to go to our backup air chain. And again, no power hit in any of this. Once we plug it back in, it will just go back up. And just filling buffers. There we go. So, if you compare the different changeover architectures, today we have dual exciters. And with that, you can have 2 air chains. You can make everything redundant if you like, or you can split it, whatever you like to do. But one key thing here to highlight is that 2 exciters are not actually fully HD synchronized with one another. If you do a changeover to exciter B, well, first you will drop RF. There will be a little bit of static on the FM until you come back up to full power. But the HD is not perfectly aligned, and some receivers will still hunt for the original HD stream for about 10 to 70 seconds. If you were to tune them off frequency back on, they'll be right back on, but they're hanging on to the last one. So it can actually take a while before your HD service is back on. So with our standby mechanisms, that becomes much better. Now, the multiple TCP option on the right, the only thing to highlight here is it has to originate from the same air chain. In order to have to state exactly the same content on both, it has to come from the same one. So it wouldn't back up the air chains themselves. So we thought, this really makes sense for maybe fleet distributions or to centralize various studios. Perhaps even put it in the cloud if you want to go as far as going that. But it could be an on-premises data center. And we want to come up with an architecture that works for FM only, which will be transmitter 3 down here, and transmitter 2A and 2B that might be in the same region with the same content. And we want to be able to we want to turn HD into a true option. It shouldn't be defining everything you do. It should just be an option. That's kind of how we look at it. Well, I don't have a whole lot of time left here. Maybe perhaps some of the discussions here could potentially be for the next discussion too. I'll just go through real quick. But one thing that we added for additional security is if you're talking about TCP/IP connections, you want them on the upstream. You want a listening socket on the upstream, not on your transmitter. And by doing so, you don't have to punch a hole into your firewall, because now it's like the normal internet paradigm. You're going out to a server. So there's no holes through a firewall or anything like that. And if any one of the air chains gets compromised, well, you can replace it. especially if it's in AWS, you go back to a backup. Yeah, so maybe it was ransomware or whatnot, you just go back to a previous state. And of course, we're working on various authentication methods with that as well. So I think that kind of gets us pretty much to the end. Maybe I'll just spend real quick where we are. April 2022, we had the system on air with KVSC in St. Cloud, Minnesota. We've demonstrated NAB. We now have the Omnia for Nautel shipping on just HD2, 3, and 4. HD1 and FM is coming. That's where really the big changes are happening. We're looking for on-air trials coming in the fall time. And we're working on standardization of this architecture so that at some point we're hoping there will be vendor interoperability. So I believe we accomplished our vision, but it's still a roadmap, of course.